Section: Introduction. In this section, we discuss the importance of strong evaluators in the development of large language models, LLMs. These evaluators are crucial during training to align models with human preferences and during inference as a substitute for human evaluation. Enhancing evaluation capabilities can significantly improve our workflow and the scientific research process, helping us develop better techniques. Typically, creating effective evaluator models requires a lot of high-quality preference data from human annotations, which can be expensive and time-consuming, especially for complex tasks like coding and mathematics. This reliance on human-generated data makes it difficult to scale to new tasks or evaluation criteria. Additionally, as new models improve, existing annotations often become outdated since they are based on older model responses. To address these challenges, we explore an iterative self-training approach that does not depend on human annotated preferences. Instead, we use synthetic data. Starting with a seed model, we generate contrasting synthetic preference pairs for a given input, ensuring one response is intentionally inferior to the other. We then use the model as an LLM as a judge to create reasoning traces and judgments for these pairs, which we can label as correct or incorrect based on our design. After training on this labeled data, we enhance our LLM as a judge, allowing us to repeat the process for further self-improvement. In our experiments, we began with the Llama 3-70B instruct model and improved accuracy on reward bench from 75.4 to 88.7, which is comparable to or better than reward models that rely on human annotations. We also review related work on LLM-based evaluators. Traditional evaluation benchmarks often use automated metrics that require reference answers, which can be limiting for open-ended tasks. Recent studies have proposed using LLMs as evaluators, either as classifiers that provide direct scores or through LLM as a judge prompting, which generates natural language reasoning to explain judgments. While LLM evaluation shows promise as a scalable alternative to human raters, many existing evaluators exhibit high variance across tasks, highlighting the need for improved methods. Synthetic data has emerged as a valuable solution for efficiently obtaining training examples, especially in situations where real-world data is hard to access or where accurate annotations are difficult to obtain. It can be tailored to specific needs, such as different evaluation criteria. Synthetic data has proven useful in model alignment and skill development, and it has been shown to correlate well with human judgments in various evaluation tasks. Our method focuses on pairwise evaluation using the LLM as a judge approach. We take an input user instruction and two possible assistant responses, then use an evaluation prompt to determine which response is better. The LLM as a judge model outputs a preference for either response A or B, often providing a reasoning chain to support its decision. This model can be used to create training data for preference optimization and is also employed in popular benchmark evaluations. We propose a novel iterative training scheme that enhances the evaluator's performance by annotating the current model's judgments with synthetic data. Our pipeline includes several steps. 1. Initialization. We start with a large set of human-written user instructions and an initial seed LLM. 2. Instruction selection. We select a balanced set of challenging user instructions using the LLM. 3. Response pair construction. For each instruction, we create a preference pair of two model responses, ensuring the rejected response is of lower quality. 4. Iterative training. We repeat two main steps. Judgment annotation. We sample reasoning traces and judgments from the current model. Correct judgments are added to our training set, while incorrect ones are discarded. Model fine-tuning. We fine-tune the model on the new training set, preparing it for the next iteration. As the model improves, we expect the training set size to grow, allowing for an automatic curriculum that enhances learning. We will now describe each of these steps in detail. Section Summary. In this section, we discuss the importance of strong evaluators in the development of large language models, LLMs, and propose an iterative self-training approach that eliminates the need for costly human-annotated preference data by using synthetic data to improve model evaluation capabilities. Our method demonstrates significant performance improvements, achieving an accuracy increase from 75.4 to 88.7 on reward bench, surpassing traditional human-annotated reward models. Section: Initialization. In this section, we outline our approach to initializing and training our model. We start by assuming access to a collection of user instructions, which can be either single text prompts or multi-turn conversations, with the last turn being a user instruction or question. These instructions cover various skills, including general knowledge, reasoning, coding, safety, and math. Next, we focus on instruction selection. Given the pool of human-written instructions, we recognize that there may be noise and imbalances in topics, difficulty, and the model's ability to respond. To address this, we select a subset of instructions to create high-quality synthetic responses for training. We categorize each instruction using a large language model, LLM, into specific areas like coding or brainstorming, allowing us to choose relevant data while discarding less useful categories. For response pair construction, we generate preference data for each instruction by creating two responses, one expected to be better than the other. We do this without human input. First, we generate a baseline response for the original instruction. Then, we create a modified version of the instruction that is still relevant but not identical. We prompt the LLM to provide a high-quality response to this modified instruction, which we expect to be inferior to the response for the original instruction. This gives us a synthetic preference that we use to create training examples, randomizing the order of responses to mitigate position bias. In the judgment annotation phase, we utilize our LLM as a judge model to generate evaluations for each training example. We collect diverse evaluations and apply rejection sampling to filter out any that disagree with the correct labeling. We then randomly select a correct judgment from the remaining evaluations. If no correct judgments are available, we discard that example. This process helps us build our final training examples of synthetic preferences for fine-tuning. For model fine-tuning, we begin with a seed LLM and train iteratively. In each iteration, we annotate training examples with judgments using the current model, creating a new set of training examples. We initialize from the seed model at each iteration. Our initial model is based on Llama 3-70B instruct. In each iteration, we use the previous model to generate synthetic preferences and judgments, followed by fine-tuning the Llama 3-70B instruct model again. We employ the FairSeq2 library for instruction fine-tuning and VLLM for inference. During training, we focus the negative log likelihood loss on the evaluation part of the training example. We select models based on pairwise judgment accuracy and position bias, with sampling parameters detailed in our training documentation. Section Summary. In this section, we outline our process for initializing a model using a curated pool of user instructions, selecting relevant instruction categories, and generating synthetic response pairs to create training examples. We then employ an iterative fine-tuning approach, utilizing our LLM as a judge model to annotate these examples with judgments, ultimately refining our model through repeated training cycles. Section: Instructions and Responses. In this section, we begin with a large collection of human-written instructions from the wild chat dataset. To select prompts, we categorize each instruction using the Mixtral 22BX8 instruct model, following a specific template, and choose 20,582 examples from the reasoning category, anticipating these to be more challenging. For these selected inputs, we create synthetic responses using the same Mixtral model. For our training examples, we gather 15 judgments from the previous model and keep one positive sample for each example. We also ensure a balanced training set by sampling an equal number of examples from different labels, such as A is better and B is better. The judgments for our initial model come from the Mixtral model, while subsequent iterations use the Llama model. Our training data is structured with a system prompt and the selected examples and responses. When it comes to inference, we utilize majority vote reasoning, where we sample multiple generations and take the most common verdict as the final judgment. To assess the effectiveness of our method, we also generate synthetic judgments from various data sources, including Help Steer 2, GSM-8K, coding instructions from WildChat, and HH_RLHF, using specific criteria and human preferences as ground truth. For evaluation, we test our self-taught evaluator model against several benchmarks, including Reward Bench and MT Bench. Our results show that our model, trained iteratively on synthetic data without human-labeled preferences, significantly outperforms the initial Llama 3 to 70B instruct model, achieving an overall score of 88.3 in the fifth iteration compared to the seed model's 75.4. We also find that our approach yields better results in evaluating harder instruction categories, although it performs slightly worse in the easier chat category. Furthermore, by applying majority voting with 32 samples, our third iteration of the self-taught evaluator reaches a performance score of 88.7 on Reward Bench, surpassing many existing reward models. In MT Bench, we report agreement rates on non-tie examples, finding that our self-taught evaluator outperforms the Llama 3 to 70B instruct seed model and matches the performance of GPT-40125. Section Summary. In this section, we describe our process for selecting and annotating human-written instructions from the WildChat dataset, generating synthetic responses, and training our self-taught evaluator model using majority vote inference. Our iterative training approach significantly improves performance on benchmarks like Reward Bench and MT Bench, achieving scores that surpass those of existing reward models, even without using human-labeled data. Section: Help Steer 2. In this section, we present the results from the Help Steer 2 validation set, as shown in the relevant table. We report the average accuracy across 2 orders and 3 seeds by swapping the response order, and we also analyze the accuracy for each order separately to check for any position bias. Additionally, we calculate position-consistent accuracy, considering a judgment incorrect if the model gives different predictions for the 2 orders. We utilize human labels from the Help Steer 2 dataset, treating the response with the higher total score as the better one. Our findings indicate that our self-taught evaluator method enhances both average accuracy and position-consistent accuracy compared to the seed Llama 3 to 70B instruct model. Next, we compare self-taught evaluator models trained on synthetic preferences from various sources. We discover that data sources targeting different skills, like coding and mathematical reasoning, effectively transform a strong instruction following language model into a capable judge. We observe that these data sources generally improve related categories in Reward Bench. For generating synthetic bad responses, we first create a similar instruction and then generate a good response for it, which we expect to be a poor response for the original instruction. Alternatively, we could prompt a language model to directly produce a bad response. Using our prompt template, we conduct training on the same reasoning-based instructions. This method yields an overall Reward Bench score of 80.7, which is effective but not as good as our proposed approach, which scores 83.8. We also conducted iterative training using labeled preference data from Help Steer 2 instead of synthetic data. The results on Reward Bench show smaller improvements with each iteration, and the final model did not surpass the performance of the iterative training on synthetic preferences. We note that other studies have used Help Steer 2 to train classifier-based reward models, achieving slightly better results, such as a score of 88.8 with Llama 3 to 70B. We then explore the impact of combining synthetic preference data with human-labeled data on model performance. Specifically, we merge synthetic preferences from reasoning WildChat prompts with the human-labeled Help Steer 2 dataset and report the results. We compare this to first iteration models trained on single data sources and select the best checkpoint for joint training. Our evaluation shows that the models maintain strong performance across various data mixing weights, with slight improvements in overall accuracy. We analyze the length distribution of our curated training set of selected instructions. The dataset exhibits a long tail distribution, with most examples being under 500 tokens. In contrast, the full dataset contains a cluster of very long instructions, including extensive coding instructions or transcripts. We also instruct Llama 3 to 70B and Struct to assess the complexity and category of each instruction, as well as the expected output length. Our analysis reveals that the curated dataset features more complex instructions related to logical reasoning and science, while the full dataset has a higher proportion focused on relationships and entertainment. Furthermore, we find that the anticipated response length is greater for the full dataset, likely due to the prevalence of lengthy and sometimes repetitive instructions. Lastly, we discuss why we do not use a traditional reward model. A robust reward model is essential for aligning language models with human preferences and enabling continuous self-improvement. However, traditional methods require extensive human annotations for preference rankings or scores, making them slow to scale across diverse domains and instructions. We also acknowledge the limitations of generative LLM as a judge, which typically results in longer outputs and higher inference costs. In this work, we focused solely on evaluating accuracy when comparing two responses, leaving the evaluation of single responses for future research.